Sensors, actuators, and onboard intelligence have not reached a level where robotic vehicles may function with complete autonomy in complex terrain. Human operation and command is still necessary for utility in unstructured environments, tasks where individual action is undesirable or infeasible, and in situations where a robot must assist and/or interface with people. Existing systems, however, typically rely on joysticks or other mechanical input devices which limit user utility and can exclude disabled individuals. The goal of our work is to develop a human-robot interface which can overcome the deficits of these systems for seamless teleoperation of mobile platforms. Specifically, we have developed a non-intrusive tongue movement-based machine interface without the need for insertion of any device within the oral cavity. The interface consists of mapping specific tongue motions by monitoring air pressure changes near the human ear and subsequently providing control instruction corresponding to that tongue movement. Capture of tongue movement ear pressure signals require the design of a pressure sensor that is unobtrusive, easy to wear within the ear, and provides precise placement to ensure signal consistency. Depicted is a design of the pressure sensor earpiece housing inserted into the ear of a test subject. The sensor includes a housing and an internal microphone. Insertion of the microphone into the ear canal also shields pressure signals from environmental noise. Signal capture was accomplished through the construction of an earpiece housing made from a mold of a test subject's ear. Testing with various size earpieces determined that the microphone housing should be placed within the ear canal at a depth of 2.5 to 12.5 millimeters, as measured from the opening of the ear canal. The microphone was sealed within the earpiece and comfortably worn by the test subject. This design mimics the very well-established structure of a hearing aid, which can be worn indefinitely. Furthermore, the process of fabricating the mold and earpiece costs less than $25 and typically takes less than an hour. A wide range of tongue movements have been shown to create measurable ear pressure signals. Based upon extensive feedback from test subjects, we have defined 4 basic tongue movements for a robotic interface. Here we show exaggerated examples of down, right, left, and up. In this example signal, a distinct change in microphone output is observed, which corresponds directly to the movement of the tongue. Not only does the trace offer a very clear indication of the onset of the motion, but its termination is also visibly evident, and nearly all residual traces of the motion are gone after only 0.2 seconds. The short time frame in which the action is mapped allows for very rapid control input. Conventional signal processing techniques, however, were generally inadequate to recognize the subtle pressure variations in the ear canal resulting from tongue movement. The ear canal itself is an interference-ridden, noise-amplified acoustic environment. We have developed an architecture based on time alignment and a new decision fusion classification strategy, with which we were able to classify left, right, up, and down movements with over 97% accuracy. The mobile robot, called WEGS 2, was selected as a candidate device for testing the performance of the interface. While the utility of our interface lends itself to a breadth of platforms, WEGS 2 is a good demonstration robot due to its exceptional mobility with few low-level control inputs. Specifically, the robot's passive mechanisms give it the capacity to move over irregular and rugged terrain using only 4 command inputs and without the need for complex control software. We propose a straightforward system designed around the 4 tongue movements described earlier for control of the WEGS 2 platform. Up, down, left, and right tongue movements in this interface control the robot such that an up movement increments the speed forward, and down decrements the forward speed, eventually leading to reverse motion. The right movement increments the heading to the right, and the left movement, naturally, increments towards the left. In this hardware-in-the-loop simulation, the robot responds to operator inputs representing the up, down, right, and left tongue movements. Note the active inputs steering the robot around large obstacles, while the robot's passive climbing mechanisms overcome smaller obstacles, freeing the operator to focus only on higher-level performance. The goal of this research was to demonstrate a new concept for human-machine interface in robot teleoperation. The system is unobtrusive, comfortable to wear and carry, and leaves the operator's hands free to execute other activities while using the system. To our knowledge, our team is the only group that has investigated the ear canal as a monitoring venue for machine interface, and has proposed the only system whereby tongue movement may be tracked without insertion of any device in the mouth. At this time, functional prototypes have been built and tested in industry at Think-A-Move Limited in Cleveland, Ohio. The first ever wheelchair controller that does not require bodily movement or oral insertion is now available commercially based on this system. Although the device is not universally applicable, we believe it lays the foundation for an entirely new generation of robot teleoperation systems.